Okay, I'm going to work a couple of the problems out from the class slides from November 1st on static equilibrium and torque. So first, the problem that's first on slide 13 about Simone Biles on the balance beam. So if we look at this problem, we've got a balance beam. Simone Biles is standing on it a distance of 75 centimeters from the edge. The balance beam itself is 5 meters long, and there are two poles, one at each side, and they are each 50 centimeters from each end of the beam. The beam itself weighs 150 kilograms, and Simone weighs 50 kilograms. Okay. And the question is, which pole exerts a greater force on the beam to hold it up? Okay, so to solve this problem, we're going to draw a coordinate scheme, define the system, and find all the torque, define all the forces acting on the system, and then define the rotation axis. So I'm going to draw these in a different color. So I've got, if we're thinking of the system as the beam, okay, now what are the forces on the beam to put it in equilibrium? I'll do those in red too. So we've got the force from the left side on the beam, which is pointed up. The force from the right side on the beam, which is also pointed up. The gravitational force on the beam, which is pointed down. And the force, the normal force from Simone, which is also pointed down. So, and let's see, this one, and this one are all normal forces, right? So a normal force from the pole, from each pole, and a normal force from Simone. Okay. So now we need to choose a rotation axis, and here I'm going to choose the rotation axis as this yellow dot here at the center of the beam, and we're going to assume that the gravitational force is applied of the beam is applied right at exactly there at that center, right? Because we treat it as happening at its center of mass. And then our torque is going to be the sum of the torques from each of these forces. So let's start with the left pole. So the left pole, sorry, I keep switching colors to make it so these will show up on top. So the left pole is trying to rotate the beam in this direction, which is clockwise. To think about that, you can think about this force being upwards on the beam. If the beam were then going to rotate due to this force around this axis, that would cause the beam to rotate clockwise. This right force here is trying to rotate counterclockwise. Simone here is also trying to rotate clockwise. And this gravitational force is not going to exert a torque because it's at the center. Okay? And so our clockwise torques are positive and our counterclockwise torques are negative. So we've got torque from the left plus torque from Simone plus torque from the right. We don't have one from the gravity because that's at the center. Our left torque is negative. Our torque from Simone is negative. And our torque from the right is greater than 0. Again, because this one is clockwise, clockwise, and counterclockwise. Okay, and so now we know that the sum of all these torques is going to equal to 0. And then now we want to have RFL, negative RFL, minus, let's see, this should be RL. R Simone, F Simone, plus R right F right. Okay. And now the distance that matters here is the distance from the center to the force. So this distance is 2. This distance is also 2. And this distance is 1.75. I'll highlight the appropriate distances on the figure to help you. So this is 2. That's this distance here. This one's also 2. That's this distance here. And this is 1.75. That's this distance here. Okay? All right. So now we want to find the left force and the right force. So now I've got this equation. Oops. My pen instead of my highlighter. So this equation is going to give us that 0 is negative 2 FL minus 1.75 Fs. That force from Simone is the force, the gravitational force. So that's M Simone G, and then plus 2 Fr. So that's our first equation. Okay, here. I'll highlight that first equation. Oops. This is our first equation that we're going to want to come back to in a second. And then the second equation we have is that the whole beam is in static equilibrium. So the sum of all our forces is 0, and all the forces on the beam are the force from the left side, which is going up. If we scroll up, we can see, I think I can squeeze them both on here. So the left force is going up. The gravitational force in the beam is going down. The force from Simone on the beam is going down. And the force on the right is going up. Okay? And now I know that 0 is FL minus M beam G minus M Simone G plus FR. So I'm going to move these two to the other side of my equation. So I have MB, that's the beam, G plus M Simone G is FL plus FR. That's my equation 2. I'll highlight it too. That's my second equation. Okay. Now I'm going to rewrite my other equation from above, this other one here. Below it, I'm going to move this second term here to the left side of my equation. So now I've got negative 1.75 M Simone G equals 2 FL minus FR. So I both moved this term to the left and I multiplied everything by -1, or you could think of it as adding this one to the left and subtracting that one from the right, from the left. Okay. Now I'm going to divide these two both by 2. So this equation will be negative 1.75 M Simone over 2 G is FL minus FR. So now if I add this equation and this equation, that's going to give me 2FL on the right side here. And then MBG plus MSG minus 1.75 over 2. These are both meters. MSG. I'm sorry that I plugged in numbers for the radii already and not for anything else, but we're going to plug in numbers for everything now. So our mass of our beam is 150 kilograms. G is 9.8 meters per second squared. Our mass of Simone is 50 kilograms. G is 9.8 meters per second squared. Minus 1.75 meters over 2 meters times 50 kilograms times 9.8 meters per second squared is 2FL. And this is going to give us that FL is 766 newtons. Okay. Now, if I scroll up to these equations above, I've got that FL plus FR is MB plus MSG. That's that yellow highlighted equation right up here. So now I've got 766 newtons plus FR is 200 kilograms times 9.8 meters per second squared. And that's going to give me that FR is 1195 newtons. Okay? So this force on the right is bigger than the force on the left. All right. And then the other problem that I'm going to solve that we didn't have time to get to in class is the one with the mast and the boom of the sailboat. It's from slide 22. So I'm going to go to a new page here. So here I have the mast and the boom. The boom is 4 meters long. I've got this rope here that is at a 35-degree angle here. Just make sure that I'm still recording. Yeah, it looks good. The boom, we said, rate 300 newtons. And the question we asked was, what's the force exerted by the mast on the boom as a vector? Okay. So in class, we found that this tension force here is 183 newtons. Okay. And now how can we find the force from the mast on the boom? Well, we're going to write that first as a vector, so it'll be Fx, Fy. And we're going to want to write all of these forces as vectors, and then we're going to say that the sum of the forces equals 0. Okay? And so what are the forces we've got? We've got the force of gravity on the boom plus the tension force on the boom plus the force of the mast on the boom. Those are all vectors, so I've written them as vectors. The gravitational force, we're going to write as a vector first. That one is 0, is the x component, negative m boom g. Our tension force is going to be Tx, Ty. And let's look at the triangle we have up here to find those. So this angle here was a 35-degree angle. I'm going to find this angle here to make this geometry a little bit easier. So since the top left angle was 35, that means that this bottom one is 55 degrees, right? Because those two together need to add to 90. And then that means that my x component here of my tension force is going to be T times cosine of 55 degrees. Cosine since it's the adjacent side, and it's negative since it's pointed to the left. And my y component is going to be T sine 55 degrees. This T is that 183 newtons that we found earlier, okay? And then this Fm is the one we're trying to find. So since we've written these all as vectors now, that gives us two vector equations. Our Fx, some of our Fx's is going to be Fgx plus Tx plus Fmx. So that's going to be 0 minus T cosine of 55 degrees plus Fmx. So Fmx is going to be T times cosine of 55 degrees is 183 newtons times cosine 55 degrees. And actually I have not put this into a calculator yet, so let's do that. So it's 183 times cosine of 55 degrees gives us 105 newtons. And then we've also got some of our y equations is going to be Fgy plus Ty plus Fmy So that's negative 9.8 kilogram meters per second squared. Oh, sorry. 9.8 meters per second squared times the mass of the boon, which is 300. Oh, I told you the weight instead of the mass. So that makes this easier. Gravitational force, which is negative 300 newtons, plus T sine 55 degrees plus F my. So F my is 300 newtons minus T sine 55 degrees is 300 newtons minus 183 newtons times sine of 55 degrees, which is 150 newtons. And so our force of our mast is 105 newtons in X and 150 newtons in Y. Okay, so that means it's directed up and to the right, which if we go back here, that makes sense, right? We've got a gravitational force pulling down, tension force pulling up and to the left a little bit, and so then to finish holding it up, we need a force from the mass that's up and to the right. All right, I'm gonna circle that, and then that'll be it for this video.